Welcome to Multidisciplinary Design Optimization, lecture number 4 on basic mathematics. To remind you briefly of what we covered last time we discussed how you can analyze functions, in particular objective or constraint functions that depend on high-dimensional input. And in addition to formula analysis, we presented sampling methods, which are particularly useful for black box functions, so functions that where you do not have the formula explicitly available. And using this data that you generate using sampling techniques, you can analyze your functions by looking at scatter plots, computing correlation coefficients, computing gradients, or regression coefficients. And you can use this information to sort your design variables according to their importance, or possibly even ignore some design variables and focus on the most relevant design variables. Today we will make a big step towards more involved subjects of optimization, and we will cover in particular what we call optimality conditions, general optimality conditions for general high-dimensional objective functions or constraint functions. By high-dimensional, I mean that they have high-dimensional input, and actually we also cover constraint functions that could possibly have high-dimensional output. That would involve techniques for boundary optima and for interior optima. So this is the structure of today's lecture. We will begin with a brief introduction, talk about general conditions of optimality, then we devote an entire chapter to the interpretation of the so-called Lagrange multipliers. What that is, I will be explaining in a second, and then give a brief introduction to the calculus of variations. Weierstrass said that a continuous function on a compact set has a maximum and a minimum in that set. To remind you, a compact set is a set or a part of your design space that includes its boundary, as opposed to an open set where the boundary is not included. So the statement by Weierstrass is not terribly surprising. However, it is good to know, it's good news, that it's actually worth looking for an optimum if you do have a compact set. And that also serves as a reminder that you want to look at well-posed problems, because ill-posed problems, for example, on an open set or on an infinite design space with a monotonously decreasing objective function, would not have a solution, and then it's not worth looking for it. We will constrain our problems that we'll be looking at to problems with an objective and a constraint functions that are sufficiently smooth, and we won't use formalism that remind you of that. So that's why we only state that here. By sufficiently smooth, what we mean here, to be safe, is that functions are twice continuously differentiable. So two derivatives exist, and those derivatives are continuous. That is important, and then you're safe to apply what you will learn in this lecture from now. The optimization problem needs to be carefully formulated, and there is a standard that I already showed to you in the introductory lecture, and I'm going to briefly show you alternative forms that can all be transformed or changed into what we call the negative null form. So the negative null form is the statement of our optimization problem as we discussed in lecture 1, and it says that there is an objective function that should be minimized with respect to some design variables. We typically omit the design variables if they are clear from the argument, but they have to be clear. That's very important. So don't write just minimize f without an argument and without an expression here that tells someone what your degrees of freedom of the optimization are. And then you add your equality constraints, which may be vector valued, so there may be many of them, and your inequality constraints, which are also vector valued, and some appropriate bound on your design space. So we call that the negative null form because the equality constraints are required to be equal to 0, and the inequality constraint function is required to stay below 0. There are alternative formulations, for example, the negative null form for maximization. Some people use that. And then there is the so-called positive null form where you require the inequality constraint function to be larger or equal to 0. And then there is also the so-called negative unity form where instead of zeros you have a 1. Where that the equality constraint function needs to be equal to, or the inequality constraint function needs to be less than. So the math that you'll be learning will be based on this. If you encounter problems that are formulated like this, you need to carefully translate them into this form. What you know about interior optima from, I suppose, high school is that a necessary condition for optimality is that the first derivative evaluates as 0 at the position or at the coordinate of your optimum. And as a sufficient condition, you would need this, and on top of that, that the curvature or the second order derivative of your objective function evaluated at the position of the optimum is strictly greater than 0. Both together would be a sufficient condition for optimality. The first condition would only be a necessary condition for optimality. So, as often, you can generalize this from one dimension to high dimensions by replacing derivatives by gradients and second order derivatives by the Hessian matrix that you also should be familiar with. So in symbolic notation we would write df with respect to df to dx vector valued, and what we mean by this is a vector consisting of partial derivatives of f with respect to each design variable, and we evaluate that at x star, and this equal to 0 would also be the necessary condition for optimality for a arbitrary dimensional input space. The sufficient condition is this here plus the positive definiteness of your Hessian matrix. So the Hessian matrix is symbolically written like this, and it is a matrix with components consisting of f with the second order derivative of f with respect to x1, and then the second order derivative mixed with respect to x1 and xd, and so on and so forth. And if this matrix is positive definite, then condition 4 is satisfied. Condition 4 and 3 together would be sufficient for an interior optimum. When the gradient of f is 0, so remember that was the necessary condition, we call x star a stationary point, and there are different stationary points that are not optimal, and whether or not they're optimal, your Hessian matrix will tell you. So let's look at different types of stationary points. You would have a local maximum if you have something like this, and this would be associated with negative definiteness. Negative definiteness means that your Hessian matrix multiplied from the right and from the left side by an arbitrary non-zero vector A would evaluate as negative. If this equation or this inequality here is true for arbitrary A, which are unequal to 0, then we do have a negative definite matrix H and also a local maximum. If H is positive definite, and the condition for that is that an arbitrary vector A that is not equal to 0 multiplied from the left-hand side and from the right-hand side evaluates as strictly greater than 0 for arbitrary A, then you are positive definite and you do have a local minimum. Okay, and well, I mean, you can imagine this this A being a vector that from the center of or this minimum here, pointing toward some other test position, and you can see it's only going uphill when this here evaluates as greater than 0. So if you have a matrix that's positive semi-definite, then it's not clear what's going on. You may have something like a ridge, or but we are for now we will only look at this case here when we have a sufficient condition for a local minimum, and this is the case when our Hessian is strictly positive definite. Because of its definition, the Hessian is symmetric, so you can interchange those derivatives if your function is sufficiently smooth, and that will make sure that H is symmetric. And you may remember from linear algebra that if your matrix is symmetric, then the eigenvalues of this matrix will be real. And in fact, these eigenvalues have a nice meaning that you can imagine. Those eigenvalues are the curvatures in the direction of the eigenvectors. And there may be positive and negative curvature, and there is a positive curvature if your function forms a valley and is nice convex, then all eigenvalues are positive. So one criterion for positive definiteness is that all eigenvalues lambda are positive. This is a nice criterion to imagine. However, it is not so nice to compute. It is actually easier to compute the second criterion, and that's a little different, but it's equivalent mathematically. So the second criterion says that your matrix H is positive definite if all of its leading principal minors are positive. So what are leading principal minors? Well, they're shown here for the matrix H, and I guess from this you can already tell the systematic. So you take the upper left component, then you add a row and a column, and look at the determinant. I forgot to say that for the first component you also look formally at the determinant, which is the value itself. And then you add lines and columns until you end up with the determinant of the entire matrix. And if all of these expressions, all these determinants are positive, then your matrix is positive definite. Formally, a minor is the determinant of a square matrix of H by deleting a specified row and a specified column. A principal minor is a particular minor, namely the one where represented by the smaller square submatrix of H by deleting the ith row and ith column. So essentially you remove something here from where you remove a row and a column that have the same number. And the leading principal minor is one that you get by only removing rows and columns from the bottom right. And there's one note on this statement here. The opposite is not true. So if all leading principal minors are negative, that does not imply negative definiteness. Okay, so only this statement is true. If they're all positive, then we know that our matrix is positive definite. Well, now we could, for interior optima, compute necessary and sufficient conditions. And unfortunately, treating boundaries is a little more complicated. So here you can tell by this simple one-dimensional example from the previous lectures that a boundary optimum may be such that the gradient does not evaluate as 0. And in high dimensions, that's of course also true. And there will be particular techniques that we'll be discussing in a second. And those techniques are really important because monotonic functions, and they are ubiquitous in the technical world, will always have boundary optima. So boundary optima is typically what you will experience in your technical analyses, and that's why it's so important that we know how to compute them and how to assess their optimality. So let's look at the more general case of interior and boundary optima. And the optimality conditions for those optima is what we call the KKT conditions. And we will devote the next 10 or 20 slides to explaining you how this works. So, but I'll give you an idea of what the result will look like. This is what we call the KKT conditions, and they are formulated using a so-called Lagrangian function. The Lagrangian function consists of our objective function, of our equality constraint functions, and the inequality constraint functions, each multiplied by so-called Lagrange multipliers. Here you can see a vector of Lagrange multipliers because you would need a Lagrange multiplier for each of the equality or inequality constraints, and that's why we arrange them in vectors. And using the Lagrangian with Lagrange multipliers, the necessary optimality conditions will read like this. So the first order derivative needs to disappear. Then, of course, the equality constraints and inequality constraints need to be satisfied. And then there is a so-called a slackness condition that needs to be satisfied, and also the Lagrange multipliers for inequality constraints need to be greater or equal to 0. But let's get there step by step. Let's get back to our two-bar truss, and then we will make things slowly more complicated to finally arrive at the general optimality statement. So the two-bar truss had one quantity of interest, the displacement, with a given formula. We had a bunch of possible design variables and a specified nominal state. And we're going to look at the constrained version of this problem, which we called problem 4. And we distinguish between version 1, where we formulate our problem with an inequality constraint, and version 2, where we formulate it with an equality constraint. They happen to deliver the same solution. It doesn't matter, because right now we are only interested in how the analysis techniques work, and it's nice that we can compare equality with inequality constraints directly. That's why we set up the problem like this. So let's look at the equality constraints first. And we simplified the objective function to this form because we're going to look at two design variables only right now, cross-sectional area 1 and cross-sectional area 2. And the rest we just collapsed into these constants, C1 and C2, which could be computed by from the design variable values of the other design variables for the nominal state. The equality constraints evaluates as this. Here's our design space definition. And now we can formulate the Lagrangian function, now being explicitly dependent on A1 and A2 and on the Lagrange multiplier lambda that we will use for equality constraints. And plugging in the expressions above will give you this expression. C1 over A1 plus C2 over A2 plus lambda times, this is the formula for the mass, and A1 over cosine alpha plus A2 minus M0. This is the mass constraint, and everything together constitutes the Lagrangian function. So let's take the derivative of the Lagrangian function. The first order derivative with respect to design variable 1 evaluates as this. So it's one term that comes from the objective function, and then there's another term that comes from the equality constraint. Similarly, if you take the derivative with respect to the second design variable, you'll get this expression, one term from the objective function and another term from the equality constraint. And now we can formally also take the derivative with respect to the Lagrange multiplier, but that will just give us the equality constraint function itself. And of course, that also has to evaluate as 0. So we have three unknowns, which would be A1, A2, and lambda. And we have three equations. And this should have a solution. In general, these three equations are nonlinear, and it can be sometimes tricky to actually come up with a solution. In this case, it's not too complicated. So what you can do here is you can solve this first expression for lambda, plug that into the second expression, and get an equation that only depends on A1 and A2, and plug that into the third expression, which was the equality constraint, and that way you can solve explicitly for A2. And if you plug that back into the first equation, you would get this result. So the solution is written here, and actually in lecture 2 we provided a numerical solution which turns out to be quite close. So the nice thing here now is that you turn a problem with an equality constraint and 2 design variables into an optimization problem without formal constraint that now depends on 3 variables, 2 design variables and 1 Lagrange multiplier. And the latter will have a solution which is also a solution to the original problem. So that's the magic of this Lagrangian formalism. So now we will make a step towards generalization. For a general optimization problem subject to equality constraints, the Lagrangian function reads like this. And the necessary condition for x star to be an optimum is that the first order derivative of the Lagrangian with respect to the design variables is 0 and the equality constraint is satisfied. And this expression here is actually equivalent to taking the derivative of L with respect to lambda. Now let's look at inequality constraints and how we treat them. Same objective function. And now we formulate our optimization problem like this with an inequality constraint. We know that by looking at the contour plots of the objective function that the solution to the optimization problem with inequality constraint will be the same as for the optimization problem with inequality constraint. We know that already. But nevertheless, we will carry out the analysis to generalize it. So the Lagrangian function is very similar now, but now instead of lambda, we write mu to distinguish between Lagrange multipliers for equality constraints and inequality constraints, mu times g. And that actually leads to the same expression as we had before, only that we have a mu here instead of lambda. And now we go through the same procedure. And by going through the same procedure, we will get the same numbers. In particular, for mu, we will get the same number that we got for lambda. So what's the purpose? Well, remember, we knew that the solution was the same. This way we showed that if a constrained optimization problem has a boundary optimum that would be the same where the solution to the constraint boundary problem formulated with an inequality constraint and the solution to the boundary problem formulated with an equality constraint is the same, then also the formalism is the same, only that lambda and mu are exchanged. So this plot we know already. And now the question is, what would happen in this case? What would happen if we had an interior optimum? So that, in other words, the inequality constraint is not active. So we somehow need a switch in our formalism that tells us we are at the boundary or we're not at the boundary. And to explain the formalism, we will again look at a specific problem, but we need to modify the problem a little bit, that we do get an interior optimum. That's why we will formulate engineering problem number 5. It says find the optimum angle alpha for best stiffness as before. That is minimum displacement. And now we introduce a new quantity of interest that measures the structural stability of our structure, something we hadn't looked at before. So remember, when you pull here, you induce a compressive normal load in this bar. And if this normal load becomes too strong, then this rod will, or this bar will eventually buckle. Something we haven't considered before, but now we're going to make that part of our model by including this constraint. Okay, so what is this constraint made of? We know that when section force 2, the section force of this bar, which happens to be F divided by tangent of alpha. So remember, F was the load applied here in the vertical direction. And the section force is F divided by tangent of alpha. If this is less or equal to the critical buckling load, which evaluates as this is not important, it's just for completeness. If this condition holds, then we're fine. There is no risk of buckling. And this is what we use to formulate our constraint. And we want this expression to be less or equal to 0. So for the simplicity of the analysis, what we do now is we replace the objective function now by this expression. Now, this is only that the terms don't get too big. It's an approximation, but it's okay. Yeah? So just think of the objective function that we had on the previous page now replaced by this, but it does the same job. And actually you can tell here that blue was the original objective function and the black dashed line is now this term here. And again, that was only to make the formalism a little leaner, and otherwise it become very messy. So now our optimization problem reads like this: minimize f of alpha subject to this inequality constraint. We formulate the Lagrangian function as objective function plus Lagrange multiplier times inequality constraint function. And this turns out to be this expression here. So let's take the derivatives of the Lagrangian function. First with respect to the design variables alpha, and then again with respect to the Lagrange multipliers, which is like saying the inequality constraint function should be equal to 0. Well, if we solve for the Lagrange multiplier and the design variable, what will happen is that we will get a solution which is on the boundary. That's not very surprising because the inequality constraint function was set to be 0. So we will definitely end up at the boundary. And this is not the optimum. So this obviously doesn't work, and we need to do something different. We need to change that formalism. So one way to change it is that we say, well, let's set this Lagrange multiplier 0, because knowing that we are not at the boundary, we are most likely in the interior. And what we do know is if we take the first order derivative of our objective function, that would be a necessary condition for optimality in the interior. And if we do that, then it turns out that the algebra is exactly the same as for an interior optimum. So here's our switch. By setting mu equals to 0, we switch to an interior optimum. Turns out that alpha evaluates at 60 degrees, and you can tell that this is indeed the optimum. Let's put these two things together. So we had optimality for active inequality constraints, where the optimum was at the boundary. And what we could observe is that the first order derivative with respect to the design variables vanished, and also the first order derivative with respect to the Lagrange multiplier vanished, which is the same as saying that the inequality constraint function evaluated as 0, which is saying we are on the boundary, and we had a Lagrange multiplier that was positive. When we looked at the optimization problem with an inactive inequality constraint, what we encountered was that the first order derivative with respect to the design variables was 0, and the Lagrange multiplier had to be set to be 0 in order to activate this. So here's our switch, and the switch says either you have to be 0 or you have to be greater than 0. And if we combine that into one formalism, we can treat both. So the formalism, the combined formalism reads, for this optimization problem with an inequality constraint, for this particular Lagrangian function, the necessary conditions for x star to be an optimum is first order derivative with respect to design variables have to vanish, sorry. And the inequality constraint needs to be satisfied. The Lagrangian multiplier have to be larger than or equal to 0. And this complementary slackness condition needs to be satisfied, which says like either mu is 0 or g is 0. So either we have an inactive boundary condition, or and therefore an well, at least with respect to this one component, an optimum in the interior, or we have an active boundary condition. And if we combine this now further with the formalism for equality constraints, we arrive at the so-called KKT conditions. The KKT conditions are an abbreviation for Karush-Kuhn-Tucker conditions. Those are three mathematicians that are associated with their invention. And now for the general problem statement, for the negative null form, we have this general necessary conditions for optimality. So first order derivative with respect to with respect to design variables of the Lagrangian function. Now with the terms for equality constraints and the terms for inequality constraints have to be equal to 0. Then we have the equality constraints that need to be satisfied and the inequality constraints that need to be satisfied. Sometimes this is called the primal feasibility conditions. Then we need also this to be true, that the Lagrange multiplier associated with inequality constraints needs to be either positive of 0. This is also sometimes called the dual feasibility condition. And then we need the switch to be either in one side or the other, which is the complementary slackness condition that needs to be satisfied. And then, of course, you can write that by omitting the argument in short form like this. But what you really mean is that these conditions need to be satisfied at the candidate point x star, the optimality of which you want to assess. The KKT conditions have a nice geometrical interpretation, and this is what we're going to look at now. But first, let's rearrange the first part of the necessary conditions by writing this. So the negative gradient is the sum of Lagrange multipliers times gradient of the equality constraint function plus Lagrange multiplier times gradient of the inequality constraint functions. So you can think of it as being a linear combination of these two contributors. So the negative gradient of the objective function should be a linear combination of the gradient of the equality constraint functions and the gradient of the inequality constraint function. So in a scenario when you have a let's look at this. Let's look at these two inequality constraint functions. So this would be G1. This would be G2, and the gradient points towards this direction, saying that the negative gradient, downhill direction, is this, as indicated here by the arrow. And for G1, the gradient reads like this, and this is the gradient in the for G2. And you can tell that minus the gradient of f can be nicely represented as a linear combination of gradient of G1 and G2. So now let's look at a slightly different scenario. If the downhill direction was the opposite direction, you would need negative mu values to represent your gradient of f as a linear combination of the gradient of G1 and G2. Therefore, mu, the Lagrange multipliers for inequality constraints, needs to be larger than 0 or equal to. So when it's equal to 0, then it's inactive, and when it's larger than 0, then it is active, and it is a part of the necessary condition for optimality. When it is negative, you may be at the boundary, but it's going downhill, so it's not the optimum. Similarly, we can see the geometrical interpretation of Lagrange multipliers for equality constraints. It's a little simpler. So if we look only at one equality constraint, you can tell that the optimality condition is that those designs that lie on this line here that satisfy the equality constraint, they have to touch or run tangentially to the contour lines of the gradient of the objective function. And when they just touch, then we have then the necessary condition for optimality is satisfied, because you can tell by smoothness of this function right where you at the point where you cannot go further downhill, which means you have to go back up. Those lines will run tangentially. Okay, you can also formally prove that, but I guess it's quite intuitive if you look at the graph like this. And lambda does not need to be restricted in terms of sign. It can be positive or negative because we have an equality constraint, so we need to stay on that line anyway. For the Lagrange multiplier of the inequality constraint, the sign mattered because you may be at a boundary position and next to the boundary position it's going downhill, meaning that your Lagrange multiplier would be negative, and this is a sign that you're not optimal. Therefore, you need to constrict your Lagrange multiplier for inequality constraints to be positive, and this does not matter for equality constraints because there is no risk of going downhill this way because you need to satisfy the equality constraint. This also works for multiple equality constraints. So here you can tell this is the gradient for equality constraint function 2. This is the gradient for equality constraint function 1. And you can form the gradient of f, or the negative gradient of f, as a linear combination of the two, and things are fine. So no restriction on the sign of the Lagrange multiplier for equality constraints. So now let's look at optimality and go one step further, look at the sufficient condition. And we will not formally prove them, but I will try to argue intuitively for the formula stated here. So what you know for interior optima, we have a sufficient condition consisting of first, the first order gradients need to be 0, and second, the Hessian needs to be positive definite, which can be translated to an expression like this. So Hessian multiplied twice by an arbitrary vector which is unequal to 0 should always evaluate as strictly positive. Then you know that there is an optimum. It's necessary and sufficient. Well, when you look at your KKT conditions, things are a little more complicated. What you want is, of course, the KKT conditions to be satisfied as a necessary criterion, and but to be sufficient, you also want to the second order derivative of your Lagrangian function to be positive, definite, on a particular space T, not on the entire space, but on a particular space T, which we will call the tangent subspace. So what is the tangent subspace? The tangent subspace is the set of all d vectors, again, which are unequal to 0, which either run in the planes of your equality constraints. So this condition says that the gradient of your equality constraint function should be perpendicular to those vectors d, and if the gradient, which would be normal to that plane, is perpendicular to d, that means d lies in that plane, okay? And the same for those inequality constraints that are active. So let's think of this here as a plane that is specified or defined by an inequality constraint function being equal to 0. And let's think of, well, this part here as a feasible design space, but as you can tell by the shape of the objective function, well, you're going downhill this way. And at this point, the Karush-Kuntaka conditions would be satisfied. Yeah? But unfortunately, you can tell that it's going further downhill to the right and to the left because the sufficient conditions are not satisfied. So, and you would discover this by probing essentially your Hessian of the Lagrangian function with a d vector that lies in that plane. So if your candidate optimum x star that you're testing lies on that plane, you know that this inequality constraint is active. You would have to make this plane as part of your tangent subspace, and by making it part of your tangent subspace, you would also look to the right and to the left and formulate a d that would point away from that x star, and you would find out that with respect to that d, the curvature would be negative, and this way find out that it is that sufficiency for an optimum is not provided. Okay, it'd be different if this objective function had a different shape. So if it ran, let's say, like this, then optimality, then you would be at an optimal point, and your optimality conditions would be satisfied. Often Lagrange multipliers can be interpreted in a nice way, and I would like to give some examples of that. So let's look at the Lagrangian formalism again. We set the first order derivative of the Lagrangian function with respect to the design variables to 0. So this equation will be satisfied at an optimum. And what we can do now is look at little increments of this expression with respect to a change of design variable values. So if we multiply the equation by a differential dx, we would end up with this. And in particular for inequality constraints, with this. So an increment of the objective function would evaluate as the Lagrange multiplier times the increment of the value of your inequality constraint function. So imagine you solved an optimization problem that satisfies an inequality constraint, and you would like to get an idea of the effect, what would happen if you relaxed a constraint. Then you can get an idea by looking at this formula. So the Lagrange multiplier tells you by how much your objective function value would change upon changing the inequality constraint function value, of course only in the linear neighborhood of the point under consideration. There is a risk in doing that, and that risk has to do with comparing different physical dimensions with each other. So if you have two different inequality constraints, and you are trying to assess which of the constraints you should relax, then you may have to scale your problem appropriately to make those Lagrangian multipliers comparable. So just think of the expression we had before, and now extend this expression by multiplying s lambda 1 as a scaling factor to the numerator and s lambda 1 to the denominator, then you can think of this being absorbed by the Lagrangian multiplier, and this would be a part of your rescaling. So by rescaling your design variables, you would change the value of the Lagrange multipliers. And what is your appropriate scale is, of course, problem dependent. This is something that you need to design, or that you need to set up such that you can use it. So this is a little similar to comparing gradients that we discussed in lecture 3. If you have gradients of different physical dimensionality, you need to normalize them carefully. And normalizing is like rescaling. So let's look at another example. Let's pose a problem that reads: find the direction of the largest or smallest normal stresses for a given stress tensor. So as you probably know from technical mechanics, a stress tensor is a very powerful construct. It tells you at a particular point of your body all stress configurations that could be realized by creating free surfaces. Yeah, so how you create your surface is arbitrary, and the stress that you would need to apply to keep the body in equilibrium will be different for each way you create that surface. But it's all included in that one particular stress tensor, and the stresses that you will create upon creating a surface with a normal vector n is given by sigma times n. And now if you want, with respect to that normal surface, the normal stresses, then you need to multiply it by n again. I'm going to draw you a sketch to make it less abstract. So let's say here's your body, and well, let's draw the body before you create a free surface. Let's say this is, well, the famous continuum potato, and you create a free surface now, which is characterized by this normal vector. And now you're first are interested in the traction values t, and then in particular interested in the I'm sorry, I need to take care of this, I guess. So, speaking of stress, where was I? So what we would like to know is in what direction, represented by n, you would find maximum normal stresses Tn. And so the objective function would be Tn, expressed by this. And well, in order to have a well-posed problem, we need to constrain the size of the normal vector. Well, I guess that's obvious, because upon increasing your n vector, you could always arbitrarily increase your value for Tn and therefore your objective function, and that doesn't make sense. So what we want is the maximum Tn subject to the constraint that your normal vector has a length of 1. So the optimization problem reads: minimize f of n, f being the normal stresses, subject to the normal vectors having a length of 1. The Lagrangian function with an equality constraint is this expression. So if we take the derivative with respect to our normal vector components, we'll end up with this expression, and optimality, that means maximum normal stresses, we will encounter in the directions of, well, I guess you already can tell, this is an eigenvalue problem. So you will encounter the maximum normal stresses in the direction of your eigenvectors. And the eigenvalues are the Lagrange multipliers. So when you take your stress tensor, compute your eigenvalues, then they are Lagrange multipliers of this optimization problems. Now let's look at another example. Let's look at a simple system of two springs, and let's look at the endpoint positions as design variables. And the question will be, where will these endpoint positions end up in equilibrium? The objective function is to be minimized and is the potential energy. The potential energy is internal deformation energy minus work done on the system, here by gravity, and can be expressed as this. So the first term represents the elastic energy of the upper spring, and this is the elastic energy of the lower spring. And this term is the work that gravity would do on the system. And the constraint would be that y and x are the same, so that those springs are connected. And well, the formal statement of the optimization problem reads like this. And now let's build the Lagrangian function in the known way. And here we add the equality constraint. And when we take the derivative with respect to the design variables, those were, well, the positions themselves, I mean, they're strictly speaking not real design variables, but using our former notion of design variable, that I guess would be, we could call them design variables here in this problem. And it turns out that, well, we have 4 equations, 4 unknowns. These are the 4 unknowns. And lambda turns out to be the force that is acting at this interface. So C is the stiffness of the spring times X is the displacement of that spring. So lambda is simply the force to keep those 2 springs connected. Now let's look at a similar problem, but this time with an inequality constraint. So think of a mass attached to a rope that is rigid in extensional direction. And the design variable now, or the optimization degree of freedom, would be z, the vertical position of that mass. And the objective function is again the potential energy, but this time no elasticity involved. And the constraint will be an inequality constraint that says that the mass cannot be lower than the length of the rope permits. So the objective function is this. This is our formal problem statement, now with an inequality constraint. And now let's take the first derivative with respect to z. And let's think of the complementary slackness condition. And well, we can easily see if mu were 0, then there is no necessary optimality condition there to be satisfied, because then we would have mg equals 0, and there is no way you can make mg equal 0. So there is no optimum unless mu is unequal to 0. Mu being unequal to 0 means that the boundary condition, the inequality constraint is active, and well, it is active with the Lagrange multiplier evaluating as mass times gravitational force, and then this is again the force acting to enforce this constraint to be satisfied. Our last chapter for today will be on the calculus of variations. So far you looked at optimization problems with D design variables, so a finite dimensional input space. It could be 10, 100, 1000 or even more, but it is finite dimensional. But now let's think of a problem with an infinite number of design variables. What could that be? That could be a problem where the design variables are functions. And for that, we need a different approach, which is called variational calculus. Let's look at this engineering problem. We want to find the best shape of a cantilever beam for minimum displacement for constrained mass. So upon that vertical load F, this cantilever beam will deform, and we want to redistribute the mass that we are in control of such that we will have maximum stiffness or minimum displacement. And we want to think of this mass as constrained. And there's another restriction. We will carry out this analysis only for rectangular profile. Well, this is strictly speaking not lightweight optimal. There you would rather use hollow profiles, but for the simplicity of this analysis, we do assume rectangular cross sections with material everywhere. Okay, so our design variable, what we can now change to redistribute mass, would be A of xi, so the height of that profile. So we can, for example, say we want less mass here but more mass here by making A smaller at this position than A at this position. Xi will be again our spatial coordinate, not to be confused with our design variable. And the design variable now is, as mentioned before, a function, which will make our objective function, strictly speaking, a functional. We will still be using little f and call that our objective function, but it is strictly speaking a functional because the argument is a function itself. And the value of that functional will be the displacement, that's our quantity of interest, the displacement at the tip of our cantilever beam, and we will subject this problem to the equality constraint that mass minus nominal mass should evaluate as 0. The dependency structure or the dependency graph looks like this. Our generalized design variable, which is a function now, so the function A of xi, will tell us what the displacement is at the tip of the beam, and will also tell us what the mass of the beam is, which will be subject to a constraint. We chose this problem because the optimization can be carried out in a nice analytical way. And one reason for this is that we can actually express our objective function and the constraint function in closed form. How do we do this? Well, at first we write down the differential equation that governs the deflection of a beam subject to a vertical load. This is something that you learned in technical mechanics, And this may look very familiar here to you, so just briefly explained, this is Young's modulus times the moment of inertia of your cross-section times the double derivative of your deflection. And this has to be equal to the moment acting on the cross-section. And the moment is simply the vertical load times the lever arm. And the lever arm is L minus the position xc where you evaluate this differential equation. So remember, we replaced x, which is typically used for differential equations or for a position in differential equations, by the variable xc, because we are using x as our design variable of the problem. If this looks unfamiliar to you, you can look it up at any technical mechanics book on beam bending. Here you can see the formula for the moment of inertia of a rectangular beam cross-section. This differential equation has actually the nice property that you can express the solution in closed form, and you do that by just integrating the left and the right hand side of it. Since our moment of inertia depends explicitly on the position, because we have a varying height, we will first divide by the moment of inertia and then take the integral on the left hand side with respect to xc, and the integral of w double prime will be w prime evaluated at xc minus w prime evaluated at 0. But since we add w prime of 0 immediately to the right hand side, we obtain this expression. And what we have here is simply the integral of this divided by Young's modulus times the moment of inertia, which depends, of course, on xc. So why is an s here now all of a sudden? The reason for that is that when we integrate, we have to introduce an integration variable. So we integrate with respect to xc, which now is in the limit of the integral. And the integration variable that we're using for this integral is s. Don't be confused by this notation. The integrand, so the expression that we are integrating, is in this notation behind our differential of the integration variable. And the reason for this is simply that we will have to work with two integrals, and it's nicer if you can see that the integration variable belongs to this limit xc here. Yeah? So this is why I write them together. So what you typically know is that ds is at the end of this expression. We just write it here, but the mathematical operation behind this is just the same. So we know that w prime of 0 is equal to 0 because we are using boundary conditions that reflect that our beam is clamped. So there is no rotation at the position xc equals to 0. And this is why we can drop this expression here. In order to come up with a solution, we need to integrate this again. And, well, we just do it the same way. And, well, the integral that is introduced is now this term. And note what has been xc here in the limit of the integral before has now turned into an r, because now r is the integration variable of the second integral. And our position variable is still xc. So we have two integration variables, s and r. And this double integral here can be further simplified. In particular, it can be replaced by this expression where we change order. We need to change order because we want to further simplify it. And we can exchange order because of this. I'm going to explain this graphically to you. So the blue integral says we integrate with respect to the variable r, and then within the integral we have another integral where we integrate with respect to s. The first integral runs from 0 to xi, and the second integral runs from 0 to r. So it's like measuring the area underneath this line here by going up like this, like within a nested loop. So you can think of taking the integral once as like going through one loop, taking it twice is going through a nested loop. But capturing this area here is the same as capturing the area here, which is the same, but here we do it in a different way. So here we integrate with respect from 0 to s, and then for a fixed value of s, we integrate r with respect to r from s to xi. And since we know that these areas have to be the same, this integration also has to be the same. Okay, so we can replace the blue integral by the green integral. And now we can eliminate this first integral because there's nothing that depends on r in the integrand. So this integral will just turn into a factor xi minus s. And this is a closed form solution for this expression, for the deflection at position xi. We are interested in the deflection at the tip of the beam, and this is W evaluated at L. If we replace xi by the value L, we come up with this expression. And this is a nice compact formula that we can use for further analysis. So our objective function, or objective functional, can now be written as a closed form solution that looks like this. Actually, to come from here to there, we also replaced the moment of inertia by this formula here. Okay, so the dependency of the moment of inertia on xi is embedded here in this a of xi, which is our design variable, or the function that we are solving for. And that sits here in the integral in the denominator. Well, expressing the constraint function, the mass, is actually more straightforward. This is simply the integral with respect to xi of rho, the density, times b times a of xi. So the b times a being the cross-sectional area. So this is a very nice compact notation of our optimization problem. We would like to minimize this expression here, representing the displacement of the tip of the beam, subject to this constraint, that the mass be constant. In the first part of the lecture, we learned how optimality conditions for discrete design variables or finite dimensional design vectors look like. And the question is now, how can you come up with optimality conditions for a function? And it turns out that you can generalize what we did before in a very elegant way to functions, and this is what we're going to do now. The optimality conditions for variational calculus are a generalization of the optimality conditions for finite dimensional calculus. And I will show you how that works. So Well, let's start at looking at a differential from one-dimensional calculus. Let's think of a df and how it is related to a dx. And I'm going to draw a little sketch so you can think of a function f of x and you would denote this df, this distance here dx, and you would say df is the derivative of f times dx. And a little more formally, this is written here. So the increment of f as a linear approximation can be defined as taking the function f at x plus an epsilon times dx. dx is an arbitrary increment, but by putting epsilon here, you would only take a fraction of it. This epsilon is really meant only as a variable that we will use in a more general context. But let's think of dx being 2. No, it doesn't matter, just any number 2. And as epsilon as being variable. And if we looked at this expression now and took the derivative with respect to epsilon, then what we will get is f prime at x plus epsilon times dx. And now let's let epsilon approach 0, and you'll end up at the derivative of x, the derivative of f at x times this arbitrary increment dx. And this is what you can call df as a linear approximation. Fine. The same thing you can do for a higher dimensional x. Exactly the same thing, only that you would now call the result of this differentiation, you would call the gradient of f. And that in a dot product with your arbitrary increment dx would give you your increment of f. So this equation here essentially is the formal definition of a gradient. So you want this here to be equal to something that you will call a gradient times the increment that you embedded in the formula in here. And this is something you can now apply also to functionals. So rather than a differential, we call for functionals the similar expression a variation. What we want is the variation at a particular point of the input space. This point is unfortunately a function, so a little abstract. And we want to evaluate this this variation with respect to some increment, and this increment now cannot be a scalar variable like this. It also has to be a function, but it is arbitrary, just as dx, and we call this a test function. And the most important property of the test function is really that it's arbitrary. So in other settings you do need particular properties of your test function, but that's not important here right now. And now let's go through the same procedure. And without evaluating this here right now, we don't know yet what it is, we say we want this to be something times this test function. And this something here is similar to a derivative with respect to a function. And we want this for optimality to be 0. So if there is no variation of your functional with respect to an arbitrary test function, then you have satisfied the necessary condition for optimality. So like similarly to saying the variation of f has to be equal to 0 for all possible increments dx, which amounts to the gradient being 0, we now say that the variation of L needs to be equal to 0 for all possible test functions v of s. And here are your optimality conditions. Let's go through the math for our quantity of interest, for which we have a explicit formula. So we want to minimize this functional subject to our constraint. We form a Lagrangian functional, which again consists of the objective function plus Lagrange multiplier times the equality constraint functional. To compute the variation of the Lagrangian, we begin by computing the variation of f. So we enter this expression here, the argument of f, into our formula, meaning that in the denominator, rather than a of xi, we will have this thing here now. Now we need to take the derivative with respect to epsilon of this thing. And we just do that very formally. So we have something to the power of 3 that depends on epsilon. So we're taking the derivative of the denominator with the power of 3, and that increases the power of 4. And then we pull out the inner derivative, which will be 3 times v of xi. So v being here in these parentheses in this expression. And that turns into this expression here after cleaning a little bit. Well, we can do the same thing for the mass equality constraint function. The derivative with respect, or the variation with respect to v of xi will turn into this expression here. And now you can isolate v of xi. And what you're left with here, the integral of this thing, is something that is similar to a gradient with respect to a function. Okay? And well, this should be equal to 0 for all possible test functions v of xi, which is satisfied when this expression itself is 0. Leading to this expression here. And that's a nice expression from which you can compute a of xi. We have our Lagrange multiplier in here that we rename to get rid of these little numbers and so on. They're just swallowed by a new Lagrange multiplier we call lambda tilde. And now it turns out that a of xi has to be equal times a constant, which is again a further processed Lagrange multiplier, times the square root of L minus xi. So this is the result. This is the optimality condition, a necessary optimality condition. And C is like a, also again like a Lagrange multiplier that we can now determine by looking at the equality constraint. So that's simple business. You plug it in here, carry out the math, and it turns out that C is equal to this expression, and you come up with a final solution that looks like this. So this is the optimal distribution of your profile height And it looks like this. Sorry, let me correct this. Here's C, here's L. We have a square root function that goes down all the way to 0. So it's not very surprising that you want to put most mass here at the root to provide stiffness against bending, and little mass here. And the optimal distribution is given by this formula. So there are more general variational problems, of course. There are in particular those that where the integrand explicitly depends on derivatives of this function that that represents your set of design variables, and then the math becomes a little more involved, and well, it turns out that actually one necessary condition for optimality will be the Euler-Lagrange equations that you may know from Lagrangian dynamics. So that's the same that you use there. And variational calculus is the basis of Lagrangian mechanics, also the finite element method, and many other problems. And people tend to discretize before they look at the variational problems, and that's why it is not very often taught. But I think it gives a lot of insight to understand how these generalizations of gradients work and how this generalization of necessary optimality conditions, what they look like. So I hope you like that a little bit. And I will summarize lecture 6. So today we learned the most important ingredient of optimization, the KKT conditions with Lagrange multipliers. They provide you the necessary conditions for optimality, and they will also give us the mathematical foundations in the next lectures to come for numerical optimization schemes. The nice thing about them is that they work on and off boundaries. And we also looked at a generalization of our finite dimensional optimization problems. We looked at calculus of variations to treat infinite dimensional problems. And for the exam, I would like you to know how this problem was solved, but you do not know about the theory of calculus of variations. So this would be it for today. I see you next week. Stay healthy and bye-bye.